So welcome everybody to the webinar about mercury-free applications. I would like to present the current state of knowledge in Metron using mercury-free applications. And I'd like to start a little bit in history as an introduction. As you probably know, polarography has a quite long history. It was invented, well, close to 90 years ago, close to 100 years ago. It was developed, or let's say developed based on measurements of the electrochemical property of mercury. And by measuring currents, it became obvious that it's possible to determine reducible, oxidizable substances on the mercury electrode. And then it became polarography. It was all about mercury for many, many years. And also we were almost exclusively using mercury electrodes for our measurements. It has a certain reason to do that. And this is what you will see on this slide. One of the reasons is the working range of the electrode. Most of the elements we are determining have a reduction potential or oxidation potential in a comparably negative potential range, potential window, more negative than 0 volt. And you can see here that the mercury electrode is covering this potential window in a very good form. And other electrode materials, for example, carbon or gold or platinum, are more suitable for the positive potential ranges and not so much for the negative potential ranges, negative and 0 volt. And this was one of the major reasons why mercury is very useful for the determination of typical heavy metals like nickel or zinc or lead or cadmium. When we compare properties of solid electrodes or mercury electrodes together, we will see a number of pros and cons for both of these types. So the mercury electrode has certain advantages. Every drop you form on the mercury electrode is a new electrode. It doesn't need any pretreatment, no mechanical treatment, no electrochemical pretreatment. You can use it instantly after the formation. It has a reproducible surface area. It has an ideal surface. We discussed the large potential window we can use. And it's application-wise very versatile. We can determine a number of heavy metals, organics, and ions. It guarantees a very large linear range. It's a volume. Metals can dissolve in the liquid mercury, and this guarantees a very good linearity. So over the years, we developed something like more than 30 applications for 30 metals in Metron, which are currently available to be used. On the other hand, solid electrodes can be used as well, but they have a number of advantages or disadvantages. Primarily, the solid electrode is depending on the treatment. First of all, on the mechanical treatment, on polishing, on how it is produced. And it's also dependent on the electrochemical treatment, activation, or what type of film are you depositing on the surface. And this electrode surface performance can change over time because the surface itself may change. The surface has a certain physical limits, and therefore also the linearity is typically limited. What we also observe when we use solid electrodes, we observe more chemical interferences than on the mercury electrode. Solid electrodes typically have a limited lifetime. Mercury does as well, but we can easily build a new droplet and then we have a new electrode. The last point I'm mentioning is limited application know-how. this starts to change. So we spent quite a lot of effort in the last years to develop new applications here in the headquarters. And of course, now it's up to you in the fields, in the various countries, also to build up local know-how to be able to run these applications. Mercury, as I mentioned, was used for many, many years as a standard electrode in polarography for metal determination. Acceptance of mercury always has been a problem. So even when I started in Metrom, which is quite a while ago, there were discussions about the use of mercury in laboratories, about toxicity of mercury, about the environmental impact of the use of mercury. But still, it was standard electrode. What we saw in the last few years are upcoming and increasing numbers of regulations that affect the use of mercury in the lab. So mercury is usually not banned. So you can use mercury in the laboratories for polarographic measurements or for other purposes, but the problems are more on the administration side. So it's getting more difficult to buy mercury. It's getting more difficult to use mercury because you have to keep logbooks, you have to track where the mercury is going to be disposed after use, and this imposes additional burdens on the users in the laboratories, and of course it doesn't help mercury to be accepted as a nice material in the laboratory. The latest development can be summarized under the, I mentioned it here, the Minamata Convention on Mercury. This is an international treaty between currently 128 countries that signed this treaty. 102 of them ratified the treaty, and the goal of the convention is to reduce the environmental impact of mercury. So emissions should be reduced, impact on the biosphere, on the environment should be reduced. And the goals to reach, or the means to reach these goals are not only, but one of them are trade restrictions. And these are the restrictions which also affect us, Metron, when we want to use and sell polarographs, because it makes it more difficult to buy mercury, especially in smaller countries. So when you go to countries where you do not have a mercury recycling infrastructure, it can be very, very problematic to buy mercury. And this is some comparably new development which came up a while ago. The treaty was signed 2017. And, but the effects become more significant over the time. So we're looking for alternatives. Alternatives are typically solid electrodes, I was mentioning that. And Metron has been developing methods and hardware for mercury-free applications for a number of years. So the early developments in Metron were conventional glassy carbon rotating disc electrodes with a mercury film. These applications were described even in the 1980s and 1990s. We have had applications for mercury and arsenic on the rotating gold electrode also for many, many years. A new introduction came in 1994. It was a so-called ultra-trace graphite electrode, a new electrode material that could be used for classical ASV applications on a mercury film, but it was the first sensor that allowed to do direct absorptive measurements on a solid electrode. All others were typically used for ASV methods, but not for absorptive stripping methods. There were a number of other approaches that we spent time on in development, but they never made it into sales. So they never reached the level of reliability to bring them to the market, to introduce them to the market. And even these early developments turned out not to be very successful in the end. primary reason was that the multimode electrode was much more reliable and versatile, and acceptance was still not as affected as maybe nowadays, and so it was more beneficial for everybody to use the mercury electrode than the new materials. We had many problems with the rotating gold electrodes. It was not so much about hardware, but mainly about the application. So many customers complained about the arsenic methods, about the mercury methods. So in the end, we did not really recommend to sell it any longer. There was a general lack of know-how for mercury film applications, also here in the headquarters. And the ultratrace electrode applications turned out to be quite complicated in handling because you had to mechanically renew the surface after each measurement, and this was also not very handy for the end users. The breakthrough was the acid trace gold, which we introduced to the market in 2014, so 9 years ago. The electrode was originally designed for the determination of arsenic because we really had a lack of methodology for determination of arsenic in water samples, and this electrode was the first one that enabled us really to sell this application successfully. We knew from the very beginning that it also could be used for mercury. For other applications, we were not so very sure. But nowadays we have a number of applications that we can run on this acid trace gold. So as I mentioned, for us it was really a breakthrough for the mercury-free applications, and it was the first reliable sensor that we could sell for arsenic for Metron. 2 years ago, we presented the 946 portable via analyzer, the first dedicated field analyzer for voltammetry made in Metron. It's based on a drop sense potentiostat with a dedicated new developed measuring cell. It's restricted to the use of the acid trace gold, so it's the first voltammetric instrument in Metron that does not use a mercury electrode any longer. And this is the hardware, but also on the methodology side, on the, we can call it software side, we have a project ongoing in Metron. It started 2 years ago. It's called Mercury-Free Applications, and the goal is to develop methods for the most important metal ions without using mercury, without using metallic mercury primarily, but the goal is, of course, to use no mercury at all. The project is ongoing for 2 years. It will continue for another year. And the goal is, as I said, to set up replacement methods for the most important applications for the mercury electrode. Most important metals. How could we identify the most important metals? So the evaluation actually is based on surveys we have been doing in the last few years. I'm sending out questionnaires at the beginning of the year to practically all representatives that sold voltammetric instruments, and I ask for instrumentation, for configuration, but also, and this is very important, for applications. And by evaluating this database, we could identify the most important metals that we need methods for. In addition, we took into consideration existing application documentation and, of course, relevance for customers. So we took into consideration that probably a plating application at the moment is more important for us than an application in food industry, because our customer base in plating is much, much bigger than in food industry. This table shows the most important metals. So they are classified in priority 1, 2, and 3. Priority 1 are those metals where we sell the biggest number of instruments for. So it's the fabulous 4, it's zinc, cadmium, lead, and copper, of course. It's iron, it's arsenic, and mercury. Metals with priority 2, we still sell considerable number of instruments for those metals, but less than for priority 1. This includes nickel and cobalt, also very, very well known and often analyzed. It includes uranium and includes antimony and bismuth. Priority 3 elements are, besides others, it's chromium, it's manganese, it's tin and thallium, it's selenium, platinum, rhodium, and vanadium. The green marked elements are those elements where we already have methods available now. So today we can say we have methods for 10 elements available that can be used. It includes all elements in priority 1 and a few in priority 2. There are a few restrictions, and these restrictions affect cadmium and iron. For these metals, we only have applications on mercury films, and we do not have reliable methods for the portable analyzer at the moment, but for laboratory instruments, we can run these determinations. The red marked elements are those for which we plan to do investigations in the near future. So this includes uranium, antimony, also chromium, manganese, tin, thallium, and selenium. For the black marked elements, we currently have no plans to do investigations, but you can see that you can expect more methods coming up in the future. When we group these applications, well, depending on the electrode we're using and on the technique we're using, we get this picture. On the right hand, you see applications on the classic carbon rotating disk electrode using a mercury film. So this is conventional technology nowadays. It's nothing brand new, but documentation has been updated in the recent years, so you really have up-to-date methodology also to run these applications. More important are the elements on the left. Here we have determinations on the acid trace gold without modification, so directly on the gold wire. So this includes methods for arsenic, for mercury, for copper, for zinc, and for bismuth. For other elements, we need to modify the sensor, so that means we need to plate typically a metal film onto the gold, and then we determine these analytes on these film. For example, lead is determined on a silver film, so silver is plated on the gold, and then the lead determination is carried out. For nickel and cobalt, we're using a bismuth film that's plated on the gold, and for the iron determination, we use a mercury film on the gold electrode. On this slide, I would like to show the goals that we followed when we did the method development. I'll try to switch off the audio here. Now I think it works, yes. These are the goals we try to follow for the method development. So the goal was, of course, to develop mercury-free methods without the use of metallic mercury, but also without the use of mercury salts. This was working in most of the cases, but not in all the cases. So in some cases, we were forced to use a mercury film because we couldn't find a method which was completely mercury-free. What sample matrices were we looking for? This was, of course, primarily organic free drinking water. It's a simple matrix, but it's also one of our most important markets. Clean water samples are one of the biggest application fields at the moment for metromoltimetry. In this context, we also analyzed water with high hardness, so water with calcium concentration at about 500 milligrams per liter, because this is typically almost the maximum you can find in drinking water samples. It can have an influence in multimetric measurements, and that's why we took this into consideration. And we also had a look into water with high salinity, seawater, because we have a number of customers in seawater analysis that use our instruments and have been using our instruments for years. We took other sample matrices into consideration if we could identify relevant application fields. I mentioned plating before, and you will see, I think, 2 plating applications in the next slides, which we also tested for in this mercury-free application context. Sensitivity was a very important goal we wanted to follow. We made our orientation on the limit values for drinking water of the World Health Organization. This is not, let's say, an legal limit in most of the country, but it's a limit that a lot of authorizations are following and to take orientation on. And so the goal was to be able to detect 10% of the WHO limit value for drinking water, if such a value exists. If possible, we took national lower limit values into consideration. So for example, for mercury, typically the national regulations are lower than the WHO limits. We also have the goal that we have 1 decade of linear range. So the goal is to have minimum 10% to 100% of the limit value as a linear range. If possible, better, but this depends on the application. Just as a quick interruption, please everybody switch off the audio in your clients, because I think some of them always switch it on again, because this interferes here with the presentation. Thank you very much. So now we come to the applications in detail. And I start with the applications on the acid trace gold without modification. I start with arsenic determination in mineral water. It's a very common method. Probably everybody knows about that. But it's a good point to start with. We can determine arsenic-free, we can determine arsenic total. We have methods for both of these species. The method is described in Application Bulletin 416. You find methods for all the species, arsenic-5, arsenic total, and arsenic-free. And on this slide, you see the limits of detection depending on the deposition time for the various arsenic species. You have methods for the 946 portable analyzer and also for lab instruments for the 884 professional VA and for the VA CompuTrace. Maybe important to know the electrodes, when you do arsenic-5, arsenic total have a comparably short lifetime. Typically we can expect that it lasts for at least 50 measurements, probably more. But it's probably the shortest lifetime for all applications that we have. We also have to be aware that the methods for arsenic-5 and arsenic total have the highest number of interferences and more interferences than the arsenic-free method. Most common interference is copper, which is common in a lot of drinking water samples, but we have methods to eliminate the interference here. Next method I would like to discuss is mercury in drinking water. Also, this is published for quite a while. Concentration here in the sample is 2.1 micrograms per liter, but of course we can determine lower concentrations. The detection limit here is typically 0.5 micrograms per liter. Important to know here is, if we apply this method to seawater analysis, we have to make sure that the most positive analytic potential is adapted, because otherwise the electrode is destroyed. Also here we have methods for the portable analyzer and also for laboratory instruments. Drinking water is also a metal which is working very well on the acid trace gold without any modification. Here the sample shows about 50 micrograms per liter. This is comparably high, but not untypical for drinking water. We had to dilute the sample because it was too high for the method we have. Detection limit here is comparably low. It's between 0.3 and 0.5 micrograms per liter. One of the latest methods we published is zinc in drinking water, also on the acid trace gold in the citric acid electrolyte. The method has a quite wide working range. It's quite sensitive. In this case, we used the method configuration for the determination of about 35 micrograms per liter. Typical drinking water concentrations are in the mid-ppb range. But the method is more sensitive, and we can go down to 5 micrograms per liter with deposition without stirring. If we do deposition with stirring, which is the normal way of doing it in anodic sterling voltammetry, we can reach much lower detection limits. But it's usually not necessary for normal samples because the concentrations are typically higher than usual. And finally, we have the determination of bismuth. I do not show the water example here because it gets boring over time, and I use here the determination in electrous nickel baths. Bismuth is one of the very common additives in electrous nickel baths. Another one is lead, another one is antimony. They are added as stabilizers to these nickel plating solutions, and this sample shows a concentration of 0.45 milligrams per liter. We only use a quite small sample volume here for this determination. The application is documented in 2 application works, one for the 884 professional VA and another application work for the 946 portable VA analyzer. Detection limits are here depending very much on the instrument because the portable VA analyzer cannot degas solutions, so we only can work in not degas solutions, and therefore the sensitivity is not as good as on a lab instrument. So these were the applications that we could run directly on the acid trace gold. The next group of applications are those metals which need a film as a modification for the acid trace gold. I start with, again, a plating application, electrous nickel baths, lead determination. This application used to be one of our cash cows for quite a number of years. In some years we sold about 10 or more % of all instruments only for this application. It decreased in the last few years, but it's still a very important application for us, and it can be carried out on the acid trace gold, in this case modified with a mercury film. The application works well, and here we have a concentration of a little bit less than 1. It's milligrams per liter. This is a typo. It's not micrograms per liter, it's milligram per liter. Detection limit of the method is well below 1 ppb. We have methods for the portable VA analyzer, for environmental samples, of course, and for lab instruments. The silver film is plated on the acid trace gold, so on the gold microwire. It's an ex situ film. That means we plate the film from a separate silver salt solution. The method does not require addition of mercury salts to the sample. So the sample solution itself does not contain silver. At the end of the working day, the silver film is removed from the electrode using the cleaning method. Determination of iron is possible in water samples as well. Here we use the acetate that is modified with the mercury film. We were up to now not able to set up a method which is fully mercury-free, so we need a little bit of mercury on the gold to be able to reproduce the method. The method is the common one we also often use on the mercury electrodes. It's the method using triethanolamine, bromate, and sodium hydroxide, so it's an alkaline solution. It's direct determination, it's not a stripping method, therefore the sensitivity is a little bit limited. So detection limit of the method is only about 10 micrograms per liter for lab instruments. The method at the moment cannot easily be transferred to the portable analyzer. It's possible, but the sensitivity is only about 100 micrograms per liter and above. So that's why we didn't make a documentation for this portable method, because we think it's not sensitive for typical customers. The film we are plating, it's an ex situ film, so we plate the film from a separate solution. It's not necessary to add mercury salts to the sample. So from the environmental perspective, I think this is a quite important point. The mercury film itself lasts for 30 to 50 determinations, and you can replate new films on an acid trace gold that has already been plated with a mercury film. So we can plate at least 5 films on the same acid trace gold without any problems. It's also important to know the film itself cannot be removed, it cannot be stripped off. So once the film is plated on the gold, the mercury will stay there. Next application is the determination of nickel and cobalt in drinking water. In this case, we use a bismuth film modified acid trace gold. And in this case, it's an in situ film. So both metals can be determined in one run. Detection limit is depending on the instrument and on the deposition time between 0.1 ppb for the lab instrument and 1 ppb for the portable analyzer. It's, as I said, an in situ film. That means you have to add bismuth salt to the sample solution, to each sample solution. But from the toxicity point of view, this is not really a problem. Bismuth is considered to be a not toxic element. Well, this has been the overview of the existing applications we have. I'd like to give a few handling recommendations now, just to give you a few guidelines when you would like to reproduce methods, when you want to work with the acid trace gold. First of all, we try to sort of standardize the application documentation up to a certain extent to make it easier for you to reproduce these methods. So each application for the acid trace gold comes with at least 3 methods. First of all, you have the so-called activation method. This is a method that you will use once in the lifetime of an acid trace gold for before the first initial use. So it's meant to activate the surface, to make it active for voltammetric measurements, and you will do it typically once at the beginning when you use it the first time. Second, you have the cleaning method. The cleaning method is used to clean or to regenerate the surface, and typically at the beginning of the working day when you want to start your measurements with the acid trace gold. And of course, we have the normal determination methods that you will use for the continuous routine determination of the intended analytes. It may be important to mention that maybe the first or the second determination after you do activation or cleaning may not show perfect curves on the acid trace gold. So there is a sort of time dependency in the behavior of the electrodes. So it takes a little bit of time until it works too well. So if the first measurement doesn't turn out to be very nice, don't repeat cleaning too often, but maybe do a few measurements to find out whether the electrode is working or not before you start cleaning or activation again. Anyway, activation shouldn't only be done once. For the film applications, so those applications that include a film deposition on the gold, they will usually come with the fourth method, the film deposition method, that is used to plate the metal film on the gold microwire. Particularly for the ex situ films, where you have a separate plating solution. Depending on what type of application, sometimes you use the cleaning method to remove the film from the acid trace gold at the end of the working day, but please read the application documentation carefully to be sure that everything is done correctly. An important recommendation is also use one sensor for one application. Or in other words, use dedicated sensors for each application. So don't use the same acid trace gold for different metals. This can cause a lot of problems, and particularly never use an acid trace gold that was plated with a film for any other metal film or for an application without a film, because this will not work. Metal films cannot be completely removed from the electrode surface. I'd like to refer here to a previous webinar that was held by Barbara a number of months ago. You can find the documentation in the sales area for download, both the video and the PowerPoint presentation slides. Finally, we would like to have a look at the applications on the rotating disc electrodes. These are not brand new, as I mentioned before, but I still would like to mention them for a number of reasons. First of all, they work well. They're established. We have redone the documentation, so the new applications come with up-to-date methodology for these metal determinations. And especially for laboratory instruments, they will not cause problems. One of the most often used methods is cadmium and lead in any type of water samples. It's a mercury film application, but in the latest documentation we use an ex situ mercury film. That means you plate the mercury from a special plating solution and then run the samples without any addition of mercury. In the older documentation, we used to mix all the samples with a mercury salt, and we changed that completely to a more environmental friendly method. Limit of detection is quite low. It's without any problems 0.2, 0.5 micrograms per liter. This is of course a method you can only run on a laboratory instrument because the rotating disc electrodes cannot be used on portable instruments. The plating solution can be used for about 20 times. The film lasts up for a day without any problems, and you can easily reuse the film manually using a tissue at the end of the day. Also very important, when you want to run these applications, you need a platinum-free measuring cell. So never use a platinum auxiliary electrode, never use electrodes that have been used together with the platinum auxiliary before, because platinum catalyzes the hydrogen reduction and can cause a lot of problems when you want to plate the mercury film. Zinc in drinking water is also nothing new. It's also typical mercury film applications run on a glassy carbon electrode. Detection limit here also 0.5, 0.05, 0.15 micrograms per liter depending on the deposition time. So here you often have more the requirement to dilute the sample than to use the sensitivity that is actually existing. Finally, here we see the overview over the existing methods we have and the corresponding electrodes we use together with the documentation codes. It includes in the last two columns the applicability to the portable instruments or to laboratory instruments. So as I mentioned before, we have the restriction that the iron method cannot be applied to the portable via analyzer with sufficient sensitivity. It works for 100 ppb and above, but not for low micrograms per liter. And of course, we cannot use the glassy carbon RDE applications on the portable instrument. For all others, we have methods for both lab instrumentation and portable instruments. And this is, of course, our goal, to offer methods for both. So what we can offer, what possibilities we have. We have methods for the most important metals in rather clean water samples. You should be aware that applications in other matrices really have to be tested. We'll see that in the next few slides, that we have to expect, or we may expect problems, and we have to test it before we sell this instrumentation. The methods are applicable for occasional use, but also for regular use. So both is possible. I personally see especially a potential replacement option for those customers who do not use the Mercury electrode very, very regularly. In the past, we have had complaints from customers who use the Mercury electrode maybe only once in a week, once every 2 weeks, and then you often have to replace capillary and needle every time you start to run a measurement. And for those customers, it could be an interesting alternative to change to one of those new methods. Restrictions. Yeah, there are also restrictions, and the most important restriction is organic matter. If you have samples with organics inside, yes, we have to expect problems. I would really like to stress this is not a problem of the metal instrument, it's not a problem of the acid trace gold or a problem of any type of sensor. It's a general problem of all VA methods and instruments. It's a problem also our competitors suffer from. They don't talk about it, of course, in their advertising materials, but it's a general fact. If you have complex matrices, contaminated matrices, you have to expect interferences, and this is something we have been facing in the past for many, many years, and it's something which will be a companion of us also in the near future with the new methods. The type of interference, the extent, depends on the method, on the analyte, and it depends on the matrix. Sometimes you have positive surprises, and a bad matrix works well, but you also can the other type of surprise, that a matrix that you wouldn't expect any type of problems doesn't work at all. Test it to find it out. Examples where you should expect problems are, for example, soil extracts, plant materials, tissue from animals or humans, body liquids like blood, food in general, strongly polluted water samples, so sewage water, polluted rivers. Yes, you have to expect problems here. There is only one solution. You have to destroy the organics, you have to mineralize. You can use a UV digester in the lab without any problems, also together with a mercury-free method. You can use other methods, but of course, it's difficult to use these methods in the field when you want to use the portable via analyzer. The special restriction is in context of organics, organic solvents in particular. We have screen-printed components on the acid trace gold, so the reference electrode, the auxiliary electrode are screen-printed. These components are not solvent resistant, so you shouldn't think about measuring metals in ethanol or gasoline using the acid trace gold. It will not work. The sensor is not solvent resistant. There are also restrictions in methodology. VA never has been a multi-element method, but for example, we could determine zinc, cadmium, lead, copper in one run on a mercury job. This will not work anymore when you use a mercury-free method. Yes, you can do cadmium, lead together, but not together with copper and not together with zinc in one run. You still can do nickel and cobalt together, but these are probably the only two couples where you can really combine methods in metals in one run. Expect that the working range of the new method is more limited than before when you were using a mercury electrode. This is mainly due to the fact that you have a solid surface and not a liquid, and the solid surface is flat, whereas the droplet has had a certain volume. We also have to expect more chemical interferences than with the mercury electrode. Also more intermetallic interferences than with the mercury electrode. We try to write precisely which type of interferences you have to expect in our application documentation, so please read the documents carefully. Lack of experience, I mentioned it before. Yes, there is a lack of experience. Maybe not so much here in the headquarters nowadays, because we spend quite a lot of time in developing new methods with the new sensors, and of course you learn a lot when you do that. But you in the field, in the applications lab, in the various countries, now it's up to you to build up this application knowledge. There is another, maybe a little bit lack of experience, and this is automation. Currently, our main focus is not to test whether all these methods work well on fully automated systems or even on online systems. Some of them will, others may not, but our main focus at the moment is simply to develop the methodology, to have methods that work for the portable instruments, for manual lab instruments. And in the second step, we have to find out up to which extent these methods can be automated. We have methods for 10 metal ions available today. You can use them. Some of them, 2 of them do not work on the portable analyzer, but the others do. So we can cover most of the important metal ions for which we sold instruments in recent years. The methods can be applied to water samples, of course. Please test other sample matrices before you sell to be on the safe side. And as I mentioned, we try to publish methods for both the lab instruments and the portable VA analyzer. What can you expect in the future? What is the outlook? Yes, you can expect more. You can expect more applications, and you also can expect more sensors in the future. So first of all, you saw that we have a number of elements on the to-do list to develop new methods for. So there you can expect more methods. So this covers methods in priority 1, 2, and 3. And we will also offer the possibility to use drop-sense screen-printed electrodes in the future. You can expect hardware coming out during this year for drop-sense SPE, both for lab instruments and for the portable analyzer. And of course, there will be application for drop-sense SPEs for quantitative measurements for these instruments as well. There is more in the pipeline, but it's too early to talk about it. I reached the end of my presentation now. Do you have any questions? So please, if you have questions, type them into the chat room. I have one question. How many times can we use silver film or mercury film on the acid trace gold? So for the silver film, I do not see really a limit. The silver film is plated at the beginning of the working day. It's stripped off the acid trace gold at the end of the working day. We currently do not really see limits for doing that. Of course, maybe if you did it 10, 20, 30 times, at a certain point, this electrode will not work anymore. And the acid trace gold has been designed to be a disposable sensor. But this can be done very frequently and very often. For the mercury film, we did some tests. We know that we can plate at least 5 films on an acid trace gold, and each of these films can be used for up to 30 to 50 measurements. And that means you can run 50 to 150 measurements without any problems on the acid trace gold. But of course, also here, we do not guarantee that you can run hundreds and thousands of measurements on an acid trace gold. it has been designed to be a disposable sensor. More questions? Nobody else? All right, if there are not more questions come up, I can only encourage you, try to use the methods, try to gain your own experience. Give us feedback, please. We're very, very interested in hearing about your personal experiences, whether they are positive or negative, it doesn't matter. Please inform us, because it's really important for us to get feedback from you in the application labs, but also from the field. Ask us if you have questions. Do not hesitate to contact us. We're happy to help you. Yes, there is another question. Have you tried to skip silver plating and try to use a silver dropsense SPE for lead? Yes, we tried to use the acid trace gold without silver for the determination of lead, but our experiences were not good. The method without a silver film does not work well. So silver on gold doesn't work well, at least as far as we know nowadays. We did not try the silver SPEs from dropsense so far. Doing more applications on dropsense SPEs is on the to-do list, but it's something we really have to find out. We have to be aware that metallic silver oxidizes when you store it. And this is something which you cannot really stop. So I'm not sure whether the dropsense SPE will show good performance or not. We will test it. At the moment, I cannot answer that question. The oxidation of the silver is also the reason why we remove the silver film at the end of the working day from the gold. So we do not want to stay the silver there for longer than necessary, especially not under oxygen in the atmosphere. All right. I think there are no more questions. Otherwise, as I said, don't hesitate to contact us. If more questions show up, send us an email, send me an email. We will answer to you. The presentation and the video will be uploaded to the sales area within the next few days, and then you have access to the material, of course. I thank you for participating in the webinar. I hope you enjoyed it, and I wish you a nice day. Hope to hear from you soon, and bye-bye.